Very nice. So I guess you are live. Oh my God, it worked. Hello, guys. Welcome to season three of Astronomy on Tap Jena. I'm very, very happy to be back here online, but online has advantages because today we have someone very special, a very good friend from very, very far away. She's not in Germany. She is in the USA. Hello, Rebecca.
Hi. I'm very excited that I get to do this with you. It has been a long time since we've seen each other, so
yes,
virtually works just as well.
Very long time. I really cannot remember. Maybe it was a conference or something.
I think it was in Copenhagen.
Oh my God, that's a very long time ago. 2018?
What even is time, honestly?
Time is relative. Yes, time is relative, definitely. Well, we have today Rebecca Larson, NSF Fellow. Welcome again. Thank you very much for your time and for joining. We will discuss very nice things about your career before you started astrophysics, after you started astrophysics, what you're doing, what is your view for the future, and about JWST, the Space Telescope, because we are very excited about that. And
yes, we are.
Look at my background.
I know. I got my necklace, to represent.
The theme tonight is JWST, and we also have a special quiz that was designed by Paul and by myself. So, guys, if you haven't taken the quiz yet, do it. I'm putting it on the chat. The link is on the chat. So have a go, and we will play the quiz together with Rebecca. We'll have a bit of fun. And also, before I forget, hello to everyone online. Very nice to interact with you again. Tell us where you're from. Don't forget to subscribe and to like and to share and to tell your friends about this awesome discussion. Okay, repost and share and everything. Good.
It has been a while since we've done our online shows, and I always was like, there's the YouTube people are like, oh, click the button, and I have no idea where any of it is. I'm just like, push like, what is the thing,
you don't know what the subscribe is.
Can't do the
it's YouTube. It's big, it's visible. It's like let me describe it for you. You open the YouTube, you go to YouTube, you type Astronomy on Tap Jena, click, and then you click on the channel and you do subscribe. And you also click on the notifications. So whenever there is a live, you will get notified, so you don't miss anything.
There's the bell. I think it's a bell.
There is a bell.
There's a bell.
Yeah. And in my other accounts, my kid has enabled these notifications for every YouTube channel you can imagine. He plays Fortnite,
Oh, right. Fortnite. You need to have those personally. You do, yeah.
So he learns from these YouTube channels, and then he also plays himself. But I get constant notifications about Fortnite, like nonstop.
You could play now. You know how. You get all of the
yes, I do. I have it on my phone, and he plays on the Xbox, and I play on my phone. We play together, and he tells me, "Come, mommy, I will protect you so they don't kill you." Very sweet. He's 10, so he still cares about me. In 2 years, it's not going to be the same.
2 years, he's going to be like, watch out, I'm coming for you.
Yes, you die. Right. So, sorry, I'm just looking at the chat. Very nice. Hello, everyone. And what is like the Wish version of the Big Bang Theory?
Ignore him.
I don't know this one, but the quiz is amazing. Have a go at this, and we will play in a bit. So let's get started. Rebecca had not a conventional career path as an astronomer, as an astrophysicist, right? So tell us a bit where you're from and what you did before astrophysics and what inspired you to get into the astrophysics field.
Yeah. So I pretty much ended up in this career path by accident. Happy accident. You know, I'm very glad that this is where I am, and I'm very fortunate that I get to do this job. But I definitely didn't start out, you know, as a kid being like, this is what I want to be when I grow up or anything like that. I am from California, so I grew up in the Bay Area, south of San Francisco and San Jose. And you know, as a kid, I really wanted to go to college. I didn't know where I wanted to go or what I wanted to do. And I just knew that I really wanted to like keep getting my education and really like learning and doing new things and enjoyed school. I was one of those kids. And so, unfortunately, like by the time I graduated high school, I wanted to go to college, but I didn't have any way to pay for it. And so I enlisted in the military at 17 because they had good education benefits and I could go to college. And I thought, you know, I don't really know what I want to do. And maybe this would give me kind of an idea of a career or get me started, or at least set me up in a place where I could, you know, like get my education and you know, be more like self-sufficient and all those kinds of things. So I actually tested all the things you have to test to join the military, and I passed this test that was like an ability to learn a language. And so a whole complicated longer story, but I ended up being a cryptologic linguist is what they signed me up for. And I at 17 was like, what does that mean? And the recruiter said, I don't know, but like very few people pass this test, so we need you to do this job. And I was like,
Wow.
So I went through basic training and I went through all this stuff, and I got placed at the Defense Language Institute in Monterey, California. So I ended up 45 minutes from where I grew up. I got really far. But I learned Arabic. So they put me through Arabic classes. I studied for 8 hours a day, 5 days a week for 63 weeks, Arabic. And I became proficient, and I was an Arabic translator, and I worked at the National Security Agency in Maryland for the government as a translator. And so that's what I was doing in the military for, you know, the 6 years that I was in. And I was constantly taking night classes. I took classes while I was doing language school. I had to get permission from commanders to do all this extra college. And I got my associate's degree in Arabic from that as like during my training. When I got stationed in Maryland, I like took night classes as much as I could. And I was, you know, doing a computer science degree for a little bit. I thought, you know, maybe I'll do like a humanities degree because it's kind of tied to the language thing. And then I took an art class, and I really was surprised by how much I enjoy. I thought I can't draw anything. I'm not an artist. But you know, I surprised myself, and I really enjoyed it. And so I decided that when I was getting out of the military after my enlistment was up, I wanted to go to college, and I wanted to open my own art studio. And so my family was back in California, and I got out and I moved there, and I was doing a business degree in entrepreneurship and a minor in studio art to open my own art studio, teach classes, have a place for people to, I don't know, throw paint at the wall because they can't do that in their own houses, you know, something like that. And that's what I really wanted to do. Well, my dad's company he was working at got bought out by Dell, which is headquartered in Austin. And then my whole family, you know, moved to Texas. And I thought, okay, well, I can't really afford California. And I was really only here because you were. And so I'll just transfer to the University of Texas in Austin, and I'll finish my degree there and continue on with my plans. Well, it turns out they didn't like that plan. The University of Texas decided I had too many credit hours because I had been taking college classes for years now, not and transferring every time. You know, this UT was my 9th school I had gone to because everywhere I was in the military, I just kept taking classes and not knowing that more college was not a good thing. And so I had too many credit hours, and I looked bad on paper to the business school at the yep. Okay, there's a dog behind me.
You are overqualified.
Basically, they were like, we don't want to admit you because you have too many credit hours and you're going to be this outlier in any of our. And I was like, well, okay, well, we'd love for you to come back for an MBA. And I was like, well, I kind of need a bachelor's degree to go back for a master's. What do you want me to do here? So they like, go ahead and apply as an undeclared major, and then you can transfer it to business school afterwards. And I'm like, okay. So I applied as an undeclared major, and I got in. And then I was like, I want to transfer to the business school. And they're like, no, they won't take you. You have too many credit hours. And I was like, what am I supposed to do now? I don't understand. Like, what does that even mean? I'll retake classes if I have to. I don't understand what you're like. I don't get this.
Yeah,
I'm
yeah.
sorry I've been in college for so long. I don't know.
I'm sorry, I'm clever. I'm sorry, I'm clever.
I'll do more for, I don't know what to say right now. And then, so the only colleges at the university that would accept me were liberal arts and natural sciences. And so liberal arts was a lot of, at the time, classes that I had tried and I had not really enjoyed. And they're like, well, you can do an economics degree. And I thought, no, I don't want to do business. I want to like start my own, like, that's not what I want to do. And so I was like, okay, well, natural sciences. And I thought, well, I had done a computer science degree, and the more programming I had to do, the less I liked it.
Yes.
Foreshadowing. And so they gave me a list of majors in the College of Natural Sciences, and it was alphabetical. And astronomy was
alphabetical. So the first one.
And I thought, I don't know, I like space. Sci-fi is like my favorite. I don't know. Classes started in 3 days. They were like, this is it. And I only had so much time left on my GI Bill before I was going to run out of money. So all this stuff that I had done to like join the military to pay for college, I was like, I need to pick a major. I need to graduate. I need a degree at all. And so I was like, all right, I don't know. And so they're great, cool, astronomy. And they like stamped the thing and sent me off to somewhere else on the campus. And then they were like, well, actually, you need to take like 2 years of physics. It's astrophysics. And I was like, I'm sorry, I have to do what? Physics? I don't know. So
oh, I'm sorry.
Surprise.
Yeah. It's so the physics and the astrophysics.
Yeah, well, so at UT, the physics department and the astronomy department are separate. And so at most universities, astronomy is like a subsection of the physics department. And so the degree is astrophysics because it's a physics degree with like a concentration in astronomy. At UT, there's separate departments and separate degrees. And so they've called it astronomy, not astrophysics. And so I feel like I was a little misled. But, you know, at the end of the day, I ended up in the astronomy program, which is a physics degree plus. And then, you know, so I, with no warning, had to take physics classes and calculus 3 and all these other things that I was like woefully unprepared for. And I failed the hell out of every test. And it had been, you know, 4 years since I had done any of the math and calculus and things for the computer science degree. And I couldn't retake them because I have too many credit hours. And so, you know, I just was so unprepared for everything. And I was devastated. I thought, you know, I've completely wasted all of these years of my life trying to get this degree. And if I can't pass this, I'm going to run out of money and I don't have any way to afford this. I don't know what to do. And so I, you know, went to someone in the department and I asked them, what the hell do you do with an astronomy degree? What even is this that I've gotten myself into? Like, this is not my plan for my life. I had no idea. And they were like, well, you can do research. And I was like, great. Can I do that now so that I know what I'm doing, or if I want to do this, or if this is even worth suffering through, like trying to make it? And so, you know, one of the professors, you know, I am incredibly grateful to him. He's like, well, if you can learn Arabic, you can do physics. And I was like, turns out that's not true. And those are different. And, but then he spent a lot of the summer, you know, hand wavy explaining quantum mechanics to me. And here's how you look at astronomy data. And here's what we're looking for. And here's this science problem. And like, if, you know, helping me learn how to code what I needed to code and make the plots and measurements that I needed to do. And he spent a lot of time, him and his, you know, postdoc and grad student at the time, like really sat there and helped me. I had no experience in this field whatsoever. And they taught me like exactly what I needed to do and how to do it. And it turns out that this project worked. And, you know, what we were trying to do was understand why, you know, stars weren't forming as fast as we thought they were. I mean, if you have a recipe for here's the ingredients you need to make a star, and you go, okay, this is how many stars you make with those ingredients, and you go out and you look in space and you think, okay, well, that's, you know, this part has all of the ingredients, but we're ending up with fewer stars than we thought. Like, what is happening? What's slowing down this process? What is interrupting it? What is going on? And there was, you know, a lot of theories, and one of them was just like turbulence, like there's just motions in space that are, you know, disrupting this process. And so we were able to actually measure direct evidence of that turbulence in clouds in space. And I, you know, had a model of with or without, and my data just landed exactly on top of the model of there being turbulence out there in space. And it was the first time any human had ever proven the existence of this thing in the universe. And that was something that I got to do. And I was hooked. I was like, this is the coolest thing I've ever done in my entire life, and I want to keep doing this. And so I failed my way through physics, and you know, and I took the astronomy classes, and I kept doing research, and I kept you know, working on this. That professor said, you know, you did the science, you write the paper. And so I got to first author a publication in my undergrad on the science that I had done, and it was an incredibly amazing experience. And so I thought, you know, if I want to do this job, I need a PhD, but if I need to get a PhD, I need to get these degrees. So I ended up at the end of the day with a degree in physics and a degree in astronomy, and I am hopefully going to get my PhD oh God, within the next few months, you know. And so I think at the end of the day, you know, I would have never guessed that I would end up here, but I am incredibly fortunate, and I am very excited for the
Very
future.
nice.
Yeah.
Well, I have to say, from what how you described your story, is that you're more than capable of getting your PhD. So
I'm not going away. I'm going to get another.
We believe in you, and I'm glad. I'm glad that you saw from the inside how astronomy works at the, you know, undergraduate level, because that's important to get contact with research and understand what is happening, and not stay on the theoretical level. That maybe, okay, it's nice to go to classes and learn physics and mathematics, but if you don't do a research project, you don't understand what really astronomers do.
Yeah,
right?
no, I mean, it's fundamentally, I mean, it's programming, it turns out. Did you know?
No,
Yeah. No, you know, like, that's not part of our classes or anything that we learn, but that's what I do on a daily basis. Is I write programs that do basically data science, and I have literally no formal training in that. I have a degree in physics and astronomy, and I make terrible code to do,
and we Google everything.
Yeah.
How to extract element from array, Python.
Yeah.
Every other week, because I forget. Like,
oh,
very basic
real. I
thing.
mean, I think I've learned how to Google the question I have, because it's like a very niche specific thing, because ultimately what we're doing are things that have not been done before. I mean, you can't just like Google, like, how do I do JWST? You can't. It's brand new, and we're all trying to figure it out at the same time. And so, like, being able to figure out the question you have and like how to get the answer you need to like make an answer for other people is a skill that is hard to learn, and is one that I'm still, you know, working on. But yeah, I think ultimately it's been a great experience, and it is hard, and I will not lie that this is a difficult thing to do, and it is to me incredibly rewarding. I think, you know, maybe one of my favorite parts is not just like learning about like our place in the universe and understanding and increasing humanity's knowledge of where we are, but also I think it's incredibly important that if we don't share what we're learning and what we understand about the universe with the rest of humanity, that there's really no point in what we're doing. And so I really enjoy doing these kinds of outreach and talking to people about space and astronomy and the new things that we're doing and learning, and trying to make it accessible, because this is what we're doing it for. We're doing it for humanity, and for people to understand and to learn and to be inspired just like we are, and to really truly understand the value of the science that we're doing, and why does it matter? Why should you care about a galaxy that doesn't exist anymore? And how does that apply to anything that we're doing now? And I think that that's incredibly important, and to me is one of my favorite things of the job, is doing stuff like this. So I appreciate you having me here.
It's excellent, and I am happy that you are here. And I just have to say that you are primarily the reason I am here today doing Astronomy on Tap, because this is how I got into astronomy after our discussion, I think in Copenhagen, right?
Yeah, probably.
Yes, yes. I think it was the first Astronomy on Tap I joined. I had so much.
Right, because we did one when we were there.
Yeah, we did one for the Cosmos meeting when we were there. You did.
Long ago.
And
Okay.
with very nice talks, and I really enjoyed the concept, being in a pub and discussing science in a, relaxed atmosphere, very basic, no buzzwords, and just have your drink, your food, talk science, relax. And after that, Astronomy on Tap was born, and then Jena, yes.
Yeah, no, I think that's awesome. I mean, we had been doing our astronomy Tap in Austin since I think 2014 was when we started it, and I've been here for 100 years, I think, at this point, doing undergrad here. I'm doing my PhD here. I've been here for way too long. But yeah, we started our show here, and it's been incredible. And I apologize to any of our audience watching. It will come back at some point when we're able. This is Jasmine.
Hello.
She's done. And so yeah, I think it's great because it's been a really incredible forum for just talking to people. I mean, I think as scientists, we should be more accessible to everyone. I mean, I think we're just people, right? I'm just a person. Like, I can just talk to you about what I do, just like you can talk to me about what you do. And I think there's a lot of value in that, and that, like, Astronomy on Tap, like you said, makes it a very relaxed environment. There is no pressure on anyone to like ask a dumb question or whatever. It's on us to really communicate and be clear and engaging, because I think science is exciting and it's fun, and I feel like astronomy is kind of like the gateway science, because it's so easy for people to just like look up and be like, oh, space, and like feel involved in what we're doing. And that's what we do. I mean, we're just like, oh, space, right? And we like, add some math and a little bit of tiny telescopes or whatever, but like, yeah, I think
code, some physics,
few extra things. But I mean, ultimately, it's like really accessible and it's really exciting. And I think it's something that, these shows, and Astronomy on Tap is now, I mean, global, obviously, but, all over the place. And I'm glad that it exists in different forms, because I don't think that any one show should be like the blueprint for how we do things. Our show is massive, and we did more things than most. And it was overwhelming and a lot of work, but it was worth it because our audience really enjoyed it. And like, we had 200, 300 people come every month to this event. It was a big event, and unfortunately the pandemic shut down our venue, and we haven't really been able to do things. We went virtual for a while, but I think that was way too hard on all of us, on top of everything else that was going on. And I would like for us to start ours again, and I am glad that you guys are still doing yours and you're doing it virtually. I don't have it in me to do the YouTubes every month, but yeah, I'm really glad that they're still continuing all around the world, and they're starting up again in a lot of places. And I think that's really important, and I look forward to when we're able to do ours again.
I'm sure once you finish your PhD, very, very soon, everything will go back to its normal pace. Yes. So now it feels a bit overwhelming. This is how it is just before you finish and you submit your PhD, and then you're like, oh my God, I have so much free time.
Well, okay. I feel like that would be the case if I wasn't trying to finish my PhD in like December, and the rest of all of the data that we have coming in from the new telescope comes in December and January.
Yes, let's talk about
the new break telescope of like 2 days, and then holy.
So you're like have 1 day of break, and then you have all the data coming in. So let's tell our audience what are these exciting data coming in. But before that, I have read in your CV that you are studying about islands of reionization. And I have a question. What are islands of reionization, and why do we care?
Yeah, so islands of reionization is what I called this research program that I led, where we were searching for parts of the universe that had been reionized. and like little pockets. And we were using a telescope in Hawaii called the Keck Observatory, and it is on an island. And I thought, clever. And so that's what that means. It doesn't really mean anything other than I wanted a fun name for my research project I was leading, and all of the data that was coming out of it. But so I do study a time in cosmic history called reionization. And so what that means is that there was the Big Bang, right? And then, over time, as stars and galaxies started to form, all of the like stuff in between galaxies was all neutral hydrogen. So like a hydrogen, atom. And what happens is a lot of the ways that we study galaxies is through like bright light from stars that are forming. And unfortunately, a lot of that light actually gets eaten up by this neutral hydrogen. Right? It interacts with it and kind of gets absorbed and scattered around. And so when we're trying to look for these galaxies, a lot of that light is blocked. And so we call this kind of the cosmic dark ages, where we can't see galaxies in their star formation. And this is typically, ultraviolet and invisible light from all these stars that are forming, all these beautiful pictures like the one behind you, where you can see these galaxies because what you're looking at is the stars and the gas and the dust and everything. And so one of the ways that we look for galaxies is we look for, signatures of these star formation, but that's all eaten up by all of this neutral hydrogen. So if it leaves the galaxy, it kind of just gets bounced around and trapped in what we call the intergalactic medium, or the stuff in between galaxies. And so at some point, we all of a sudden start to see all of these galaxies and all this light. I mean, over time, we start to see the light from these galaxies, and we call this cosmic dawn, right? The dawn of, we're terrible. Whatever names, but like the dawn of our ability to really study the cosmos. I don't know. And right, and so like it's because we can now see this light, because all of this stuff in between galaxies has been reionized. Hydrogen has been reionized, meaning it's been broken up into its proton and electron, right? So instead of being a hydrogen atom, it's been separated, and the light no longer gets trapped by all of these atoms in space. And so we're able to see the light from these stars. And so we don't really know a lot about this process. We don't know what did that. We don't know how long it took. We don't know when it started. And all of these questions are still pretty unanswered. And the problem is we're trying to look further and further back in time, and in trying to like search for galaxies that are in this time frame of the universe. And we need to do that by looking often at their stars, right? The light that's ultraviolet and visible from these galaxies, from the stars that are forming. It's the brightest things that we can see. But the problem is this thing that we call redshift in astronomy, where the further something is away from you, the light gets stretched out, right? So as the light left these galaxies 13 billion years ago, it's traveled to us through space, but space and time has been expanding. And so as the light's traveled, it's been stretched and expanded over those 13 billion years as it traveled to our telescopes. And so what ends up happening is these short wavelengths of ultraviolet light that we're looking for have been stretched so far that they now hit our telescopes in the infrared. And so what we need is to look in the infrared for these distant galaxies, even though the light that they're emitting was ultraviolet. It's just when it comes to us, that's how we see it. And so we can tell how far away a galaxy is by how much like this light that we know is ultraviolet light is, like how far down the spectrum has it shifted to the red part of the spectrum, or red shift. And so that's a measure of how far away these galaxies are. And so what we need is to look in the infrared for early galaxies. And the infrared, unfortunately, maybe gets absorbed by the Earth's atmosphere. And so while breathing is nice because we have an atmosphere, it is difficult to do my science from the ground, because I need to get infrared photons, but they are getting absorbed by the atmosphere. Now, there are telescopes that can do this. And so the Keck Observatory in Hawaii is one of the biggest telescopes in the world, and it is sensitive enough to like, and has instruments that work in the infrared, and we can, stare for a really long time and hope that a few of them, kind of come through, and, in between all the, like the atmosphere, parts that block the spectrum, maybe we'll be able to see some of these galaxies. And so that's what I've been doing for the past several years is I've been leading this program called Islands of Reionization, because we think this process happened kind of like Swiss cheese in a way, where like at some point all these like little holes and bubbles started to pop up as parts of the universe ionized, and then like that ionization kind of like spread, and then at some point all of the stuff in between galaxies was ionized hydrogen instead of neutral hydrogen. And so we think that parts of the universe that did this first, that the parts that are ionized early on are the parts that are probably more dense, right? The thing behind you is a cluster of galaxies. And so early on in like, there's thousands, I don't even know how many are in this one. This is the SMAX cluster from the PRO release from JWST from NASA, some of the first images that they released. And so like early on in the universe, these were, like galaxy like group, like over dense parts of the universe started to form these things 13 billion years ago, and then they all start to kind of fall in and get bigger and bigger and bigger. And so these clusters early on were probably denser parts of the universe, and so these parts we believe were where the universe started to ionize first. And so we're looking for little pockets of the universe that were ionized and hoping to see like any of this light that's been able to get out because of that. And so that's what I've been studying. And like I said, it's really, really difficult from the ground. So we want to get away from the atmosphere. We want to go to space, right? And so Hubble for a long time has been able to do this, but it only goes so far into the infrared wavelengths. And the problem is you need like higher resolution. And so the resolution of your images, like how resolved they are or how much detail you can see, is based on the wavelength of light you're looking at versus the size of your mirror, basically. And so Hubble is pretty small, and it's looking at longer wavelengths. And so the beautiful pictures you see of Hubble are ultraviolet and visible, because that's its niche where it's very, very good, is because like that's the resolution of this telescope, is to look at these things. It can look in the infrared. They put a camera on it that can look in the infrared, but it's kind of it's a little blurrier, and it also doesn't quite go out as far into the infrared portion of the spectrum as we need to study further and further back. And so what we really needed was a larger telescope outside of the atmosphere. And it turns out,
yes,
I really got it.
We got
it. And for years and years, me personally, I mean, like this has been happening for a very long time, and I got here late, but like this telescope is insane and phenomenal. The James Webb Space Telescope, or JWST, is a giant space transformer infrared telescope that lives 1 million miles past the moon in space around a position, of stable gravitational pull, and looks out into space with a, massively bigger mirror than Hubble, and specifically designed to work in the infrared. It is everything we needed to study the early universe and a lot of other science that we can do, but personally, that's what I'm excited about, right? And so now what's happening, and we've gotten data starting in July, what's happening is all of these galaxies that we have struggled to see and struggled to detect and couldn't even look for or look at in any kind of detail are there, and we're seeing them, and it is insane, and it is exciting, and it is revolutionizing my particular subfield of astronomy, because for the first time, not only can we find these things, but we can study them in detail, because we have detailed images and resolution. And one of the cameras, NIRI, on this telescope is looking at wavelengths that we haven't been able to look at before. And so for the first time, we're able to really study any of these things that existed in the first billion years of the universe. And it is so cool and so exciting. And I am so fortunate that I'm on a lot of these teams, and we're taking this data and we're doing the science, and like, and it's real, and it's happening, and it works, and it's so cool.
It's amazing, isn't it?
Yeah.
I think it's like a golden era for infrared astronomy, for sure. And not infrared astronomy, for astronomy in general, because we were never able to see that far back galaxies.
I think it's also,
stars.
it's also important to point out that like we're not just using this one telescope to do this. We're using Hubble, we're using JWST, we're using ground telescopes, we're using radio telescopes that look at different parts of galaxies. Like that we're looking at the same galaxies at multiple parts of their spectrum, right? So, stars emit light at this wavelength, gas and dust emit light at this wavelength. And so what you're seeing in these images, like the one behind you, is some of the light that you're seeing is stars, and some of the light that you're seeing is dust and gas. And it's all of the things that make up these galaxies and everything else that's in space. And we're getting to study them at all of these different wavelengths. And we've really kind of unlocked this portion of the spectrum we haven't been able to study in detail before. And so JWST is fantastic and it's enabling all of this extra science, but it's also even more important to use it and be prepared and to use it in tandem with all of these other facilities that we have. And while it's important for me for galaxies that are far away, but it also has the ability to look at atmospheres of planets around like other stars other than our sun. It can detect, all kinds of things and do all kinds of astronomy that we haven't been able to do before. And I will always scream about the galaxies because that is what I'm excited about. But I think, some of the beautiful pictures, we've taken a beautiful picture of Jupiter in the infrared and Neptune, and we can see the rings, right? The rings are so visible of Neptune in the infrared. These are wavelengths of light that we haven't been able to get these beautiful pictures of before. And, we're finding, black holes in galaxies and some of these things. And I think all of the press releases that are coming out of any of the teams or NASA or ESA or CSA or any of them that are doing these really cool programs and this amazing science. I think it's fantastic to get to see a comparison of what we're seeing now and what we knew before and all of the things that we're learning.
Do you think we will be able to see the first stars forming or the first galaxies forming with this kind of data?
Yeah, so I feel like we'd have to be pretty lucky. So the first stars and the first galaxies formed really, really early on. Probably maybe within the first 100 million years. And so we'd be looking for something that's so incredibly far away and so incredibly faint. But what we might be able to do is like with the cluster that you have behind you, I'm going to keep using this because it's the thing I'm looking at right now.
That's why I put it there, so I can, help you.
I did not think about visuals at all, but
I like your background. I very much like your background. All these little things.
Yeah, so with these clusters of galaxies, I think there's been a lot of talk about gravitational lensing, and so if you see, there's some of these galaxies that look a little bit stretched and warped, and it's a little bit weird looking. And what's happening is the gravity is actually bending the light of the things behind it, and so those things that are warped and stretched are actually physically behind this cluster of galaxies. Oh my God, my camera's inverted. Right, are physically behind this cluster of galaxies, and what's happening is the light is actually bending and stretching around it, and so what you're seeing is these arcs as it goes around it. So what you're actually able to see is something further away than the cluster that's kind of in front of you. And so what normally happens is if you're looking out into space, space doesn't care where we are, right? We can't see things that are behind other things because the bright thing in the front of you is in the way. But clusters like this and the gravitational, yes, exactly. The pull of these galaxies is actually magnifying more distant galaxies behind them. And it's magnifying. It's not just bending and stretching. It's actually enhancing it. And so those galaxies are further away and we're getting details from them because of this that we wouldn't be able to do. So it is possible that we would, with the assistance of something like this, be able to see something even further away than we could probably see with JWST. I think we would need an even bigger infrared telescope to see the first stars and the first galaxies unassisted. And so let's keep going, but make more, but
make more telescopes,
like LUVOIR or any of those things. But I think I hope that the things that we're learning now are already changing our understanding of the early universe, and it is possible that we will be able to at some point, and with some of the very deep fields. And we have one of the first deep fields is being taken in January. That's a program that I'm on called the Next Generation Deep Field, or NG Deep, and that's looking at the Hubble Deep Field, and trying to do another deep field with JWST, where any of this data that you're looking at right here are very short exposures comparatively. I think this is an hour per filter or something like that.
That's
and
very
so
short compared to what Hubble
the
can
Hubble
do.
Deep Field is thousands of hours of exposure, thousands of hours of exposure time. And already the things that we're seeing with JWST are blowing our minds and are phenomenal in the detail and all of the things that we're learning. I mean, there are so many galaxies. Like, look, just every single dot in that image behind you that doesn't have these spikes, like that's a galaxy. And like the tiny ones are further away or smaller, and they're all different. And we're learning so much. And that is very short amount of time of looking. And so if we build up another deep field with JWST, what are we going to find? Like, what are we going to be able to see that we've never been able to see before? And that, I think, is super exciting. And like, our data comes in January and we were like, not ready, right? But like, I mean, I don't know if I'm emotionally ready, but like every time we look at any of our data we have now, so I'm part of a program called the Cosmic Evolution Early Release Science Survey, or CERS, CERS. And we took one of the biggest images with JWST so far, and of galaxies. I mean, we took a big image of the sky, and there are so many galaxies, and we're also finding galaxies early on in the universe that are brighter than we expected. We never thought we'd be able to see galaxies as distant as, 300 million years after the Big Bang, like we're seeing now. With the data we had, we thought we would need to go deeper, but these galaxies are so bright, and like, why are they so, we don't know. We didn't expect it, and so I think some of the best and the most exciting and fun parts of the job are when you get new data and you're like, what the hell, right? Like this, like, what is this? We did not expect it. And like, to be wrong about our theory, sorry, theorists, to be wrong about the theories and like all of the simulations and all of, like, if that's wrong, that's fun, right? Like, this is new. This is truly new science that we did not understand. And we are learning more about the universe every single day with all of the data coming in from this telescope. And it is changing fundamentally our understanding of how the early universe was. And that's
and how it will evolve, right? Because if
these
galaxies
start, how did we, the whole process of getting here, right? So how did that reionization, we didn't know, and like we thought we knew, but we were wrong about some things. And so it's possible that these galaxies early on are just different. Like, they may make stars faster or easier. They might, have a special recipe, to make these stars that are emitting all of this radiation that is ionizing the universe around them differently than the galaxies that we see close up. So our expectation that we would need certain things to see these galaxies could be wrong. Like, it just could be wrong. They might just be different kinds of galaxies, and the physical processes that are happening in this galaxy are different. I mean, that is very likely true, especially with some of the things that we're learning now. And so maybe perhaps we're seeing things because something is different early on in the universe with how, stars are being formed, because there were less elements, there were less what we call metals, which is literally anything bigger than hydrogen and helium, because why call things any other names? And so like these first stars only had hydrogen and helium and, like trace amounts of lithium from the Big Bang to form. And so when we're looking for those first stars, we're looking for stars that only contain those elements. And what they had to do is they had to fuse heavier and heavier elements in the cores of these stars and then explode. And that's how those elements exist in the universe. And so we've had to do that multiple times for our universe now, with all of the elements that we have are formed in stars and neutron stars and explosions and all these other things in space. But early on, that hadn't happened yet. Like, so what we're trying to understand is like, well, maybe the way things happened then is different because the ingredients were different. And so, I think that this is a really cool, exciting part about what we're doing galaxy-wise. I mean, we're able to like detect, like, I think we found methane, and all kinds of stuff in an atmosphere of a planet around another star. There's all kinds of really cool science that's happening with this telescope. I just know more about galaxies, so that's what I'm going to yell about.
So do you think, since you mentioned planets, do you think I will be able to find signs of life?
So I will caveat this with, I am not a planetary scientist, and I am not sure what constitutes like a trace of life. I think that what we're going to be able to do is actually study in detail the chemical compositions of an atmosphere around a planet, which also tells you a lot about what's on the surface of that planet for the first time. And we've been able to do this a few times, and again with like kind of this whole lensing thing that happens to enhance it, but we're able to do that now just like basically kind of on its own, I guess, directly able to to measure these atmospheres. And I think what we're looking for is maybe a signature in an atmosphere that's similar to our own. I mean, I don't know, the exoplanet scientists, the planetary scientists that are taking data from this telescope are starting to release their results. We're starting to get those results out. So I'm not sure exactly what they found. They haven't put them out yet, but every time they do, it is exciting. It is exciting. It is insane, and it is really cool to see again another field of astronomy that's being completely revolutionized. Like, we have not been able to study these things. We've been able to like try to even detect these planets around other stars, and now we're actually able to study details about them, and that's something we've not been able to do either. I mean, we've been searching for these distant galaxies, but we haven't been able to study anything about them. We don't know what they're made out of. We don't know anything about them, but now we are, and we are doing the same thing with planets. And I think that that's super cool too.
Super
right?
cool.
So I think
Yeah.
that, you know, it's important to acknowledge that there is all kinds of science being enabled by this telescope, and it is not built for one purpose. And it's also going to be and being used for things we didn't think were going to be possible. I mean, personally, I keep freaking out about just the like tech pictures they're taking to make sure the freaking telescope is focused is full of galaxies in the background.
Yeah.
Like, there's all this free data about galaxies that we just didn't. I mean, that's not even a science image.
Yeah.
I think I had helped process and all this stuff, that image, when we had gotten the full data down from the archive. And I was looking at it, and I was just, how did we, this telescope is crazy. Like, it is insanely detailed. It is insanely, you know, sensitive to finding like faint things out there. And I think, you know, it is operating better than our best expectations, but it's also brand new. And there are really unexpected difficulties with the data that we are still trying to figure out. And we are all working at the same problem in separate ways. And yes, Ryan, every field is a deep field now, which is insane. Like, it's insane. What is a deep field going to look like? Every time we look at our images, we're like, oh my God, NUD is going to be insane. It's going to be insane, right? Like, I don't think I'm emotionally prepared for what that picture is going to look. Now I'm also worried, like, is there going to be any space, or is it just going to be all galaxies, the whole thing, right? Like, how much are we going to see when we actually use this telescope heavily to study one spot on the sky? I think that that's going to be.
And you know, in some images, for example, in the quintet, you could see galaxies just behind the big galaxy. So you have all these galaxies overlapping. For astronomers, this is a nightmare, guys. This is absolutely
I was like, what are we going to do?
Because I will explain. We want to study, for example, how much light comes from one galaxy, right? Let's say this red one here, okay? But because James Webb is so sensitive, you can see galaxies from the back of it and from the front, and they are all in the same line of sight. So the light you get is like addition from the light of the galaxy you want, plus all the galaxies behind it and whatever is in the front. And it's very difficult to separate that. So yes, there are many teams that are trying to do that with different methods, and we're working on that, but it's a nightmare, really.
Yeah. It looks really pretty,
yes.
But scientifically it is very difficult to disentangle which light is from which galaxies, like Eleni's saying. And I think it's a weird, unexpected problem for us, and is stressful, but it's also like not the worst problem to have. No. You know what I mean? Before, you know, we've had infrared telescopes in space before, and I would be remiss if I didn't mention my love for Spitzer. Spitzer is a space telescope that was actually following, you know, trailing behind Earth's orbit around the sun, and it is now trailed so far that it is basically almost on the other side of the sun from the Earth, and we can't really talk to it anymore because we can't turn it to face the sun to talk to us. And so maybe when it comes back around, you know, we'll be able to talk to it again if it's still alive. We don't know. So this telescope was also pretty small, right? So small like Hubble, but also built to work in the infrared. And so what ends up happening is that we have really low resolution images. And so a lot of the times what we were running into is we had a Hubble picture, and then we had a Spitzer picture, and we couldn't tell how, like, it's all blurred out because the pixels are much larger, the resolution is much lower. And so you were having this problem. It's like, okay, I see that there's two galaxies in my Hubble image, but it's like one blob in Spitzer. And so I don't know how much of that blob is this galaxy or that galaxy, and it became difficult. Now with JWST, we're like, oh, it's four galaxies. Oh, okay. Well, and now what's happening is, depending on which, wavelengths that you're looking at, you're like, oh, well, now the Hubble is a little blurry compared to the JWST image. And you're like, okay, well, maybe the Hubble was wrong. We thought this was the truth, and it's not. There's actually 3 galaxies in there instead of 2. And now we're like, oh my God, I know everything.
So there is no absolute truth, and it all depends on your resolution and sensitivity. There you go. And the wavelength. There you go.
That's a great takeaway for science. We don't know.
So that is the takeaway message from the takeaway message.
New things.
Yeah.
Yes.
The takeaway message is that JWST is awesome, and this is only the beginning. And actually, I was watching a tutorial how to make these images, like the one just behind me, and it's amazing how much effort goes into making a public release image.
It is, yeah. I've been sort of playing around with this with some of our data from some of the programs that I'm involved in, and I've had a great time. I mean, the little artist in me that never got to be an artist and have an art studio and all this other stuff is like, oh my God, I get to play with space pictures now, and this is really, really exciting. And so I've been a little distracted often by like actually editing some of these photos so that they I mean, it's hard because the actual images are black and white, right? I mean, we're taking the black and white pictures with the telescope, but what we're doing is we're putting filters on the telescope that only look at a certain part of the spectrum. And so typically with Hubble, we were looking at visible wavelengths of light. And so you're like, this one is blue, this one is red, this one is green. These are actually, with your eyeballs, you would see red, blue, green. If you had a Hubble eyeball, like this is what it would look like to you. And so we were coloring the pictures that looked that way. We cannot see in the infrared as humans. And so these colors are specifically chosen to mimic the same. Shorter wavelengths are blue, longer wavelengths are red, and to put them into color so that we as humans can kind of really truly understand what they are. And we're basically taking like some kind of data and we're translating it. And so I feel like in a weird, I don't know, poetic way, all of my lives are coming together where I get to translate things from one image language into one that we can understand and see, and edit those pictures and then talk about the science of what we're actually seeing. And so it's been a really oddly, uniquely fun experience for me. And I think if there's anything that like maybe to take away from this is that like science is incredible because our understanding keeps changing. And I think that that's the important part, is that when we learn something new, we learn something new. We aren't just entrenched in what we thought was the truth before. I think being wrong is the exciting part about science. When we are wrong, we learn. And I think that that is the fun part of what we do now. And I hope, and I've been excited by, but I hope that the public really wants to come along on this journey with us as we try to figure out anything at all about the early universe and about other planets and about things that we will never physically be able to go to, but we will understand about how we got to be where we are now. These galaxies are going through the same process that our own did, and we're trying to understand why are we here, and is that possible that it happened often? Is it weird? Are we an outlier? Are we normal? Is the Milky Way something special? We don't know. And so we need to understand a lot of galaxies and put everything kind of in a cosmic context. And that is what we're trying to do as astronomers and scientists, is to try to really understand why and how we got here.
I think that's amazing what you said, and we keep this the takeaway for today. And my last questions before the quiz, because I have a quiz for you all. My last question is, what do you think is the next big discovery? Anything related to this awesome telescope or not? Anything.
Oh. Or anything at all.
Or anything at all.
Oh.
Yeah.
I'm gonna be a little bit, don't tell my boss. I think what's going to be really, really cool is some of our studies of the moons of the planets in our system. I mean, I think some of the spacecraft probes. I don't like the word, but like you know, like some of the satellites that we are going to be sending out are going to go study Europa. I mean, this is a moon that's covered in ice but has an underwater ocean of water, like underground water ocean. I mean, this is where we think life started on Earth, is underground in the ocean. And so there is a moon in our own solar system that has water deep down underground in the core where it's probably warm. So these are probably places where we most expect life to have started here. And why wouldn't it start there? I mean, these are missions that we are sending a spacecraft out to that moon to study it in detail. And I think, you know, we're also sending, you know, the Dragonfly mission is going to fly around on the surface of Titan. I think, you know, like we're studying some of the moons of the very big planets in our, like the big gas giant planets in our system, and these are probably the most likely places of other life, you know, in our own solar system. And I think that that's really exciting and really cool, because those are gonna, you know, be even more, in my opinion, like maybe revolutionary to our understanding of how like we personally as humans and as life got here on this planet. I mean, we think Mars might have in the past, but it lost its atmosphere. Venus maybe could have in the past, but the greenhouse effect took over, and now it's like all atmosphere, and it's very acidic and dangerous. And so, you know, while these two planets next to us are like decent analogs for Earth itself, I think that, you know, these moons are warmed up by the, you know, the gravitational pull and the tidal forces of, you know, Jupiter and Saturn and things like that, and also potentially have all the ingredients that we think we need for life. And or one of them has methane oceans. I mean, maybe there's life that way. You know, we don't really understand. I think that the fact that we've just recently approved a lot of these solar system missions to go study those is really, really exciting.
Yes, amazing. And you know, the search for life can be any type of life, right? It doesn't have to be human type of life. We just don't understand it yet. So maybe that will be the unexpected big discovery. Awesome. Yeah. Good. Thank you very much. Guys, if you have any questions for Rebecca, write them in the chat. And I will post again the quiz link, and now we play. So let's have a sip of alcohol because it's happy hour.
Oh, okay. Well, I'll pull out my iced coffee for you.
Yes, it's not Irish coffee. Eh?
It is 1 p.m. No.
Yes, okay.
I like still have to work today.
You know? I'm sorry, but in Germany that says nothing. You know, people can drink from time.
I'm trying to present a responsible attitude here, but I mean, I was in
I'm a bad influence. I'm a bad influence. You know, 7 years in Germany have ruined me.
You've gone native.
I was like that before. So guys, let's see if you have typed anything. Yes, every image is a deep field. We agree. And yes, doing math is fun. We can agree doing math is fun. I'm just reading a bit the comments. I don't know.
Do we agree?
What is Lords? I don't know what Lords is.
It's a game I play.
I don't know that.
No one should play the game.
No, okay. And right. So let me find how to share. Right. I want to share this one. I don't want to give you the answers. I hope you know the answers. Okay, some of them have more than one answers. Okay, you can have 2 or 3 answers.
Wait, I'm being quizzed now?
Yes, listen. You already said you already answered while we were talking. So half of the quiz you have answered. If the people have been paying attention to you, they will know at least a very big percentage.
You said grade, then.
A lot of things. So guys, get ready, log in, start playing. Let me see again. Hello Manos from Greece. Hellas, yes. How do I share? I want to share, yes, this one, hopefully. No, wait, I don't want to share this yet. Excuse me, guys. It's, you know, it's the first one of the season 3. I'm a bit nervous.
No,
I found it. Yes, this is the one.
You got it.
Hopefully now you can see. Right. This is our quiz, designed by Paul Hombach from Bonn. Thank you very much, Paul, for the questions. And myself. You have to type your email and then submit the form. And I will reveal the winner privately because, you know, we are all about data safety here. Right. So, question one. Is it question one? Yes. The JWST is in orbit around the Earth, Mars, Lagrange point L2, or the Moon. And if you were listening to Rebecca, you would know it's not Mars, for sure. It's not the Moon, for sure. It's, what is it, Rebecca? Is it the Earth or is it Lagrange point L2?
So it is actually L2, which is a position in space outside of both the Earth and Moon orbit around the sun. And so, you know, the Earth goes around the sun and the Moon goes around the Earth as it goes around. Well, there is a point out here that goes around the sun with us, and that is called L2. And in fact, JWST is out at L2, and it actually orbits around it so that we can actually kind of see more of space, and it orbits around to like give us a better viewpoint instead of just staying stationary there.
That's very nice. I like this visual. Everything is going
on. It's hard because we're camera, and I'm like, oh.
That's super cool. I'm in the wrong room now, but in my other room where I usually do these lives, I have this solar system with the planet. So I just need to add a few more little things. That'll be nice.
But it's got to orbit kind of like this way. Yeah.
Yeah. Very nice. So now you guys know. Right. JWST observes at which part of the electromagnetic spectrum. And if you have not seen the telescope, this is how it looks like. That's not an actual picture of it in space. It's a drawing. Okay, just to...
But yes, that is what it looks like.
That is what it is. This is the mirror. These are the shields. These are the instruments, I guess, down here. Yeah. So, is it the optical, what we see with our eyes? Is it the infrared, the radio? We don't see radio. Okay, we hear radio wavelengths. You know, we hear the radio. We have telecommunications. We have mobile phones, but it's not that. And we have X-rays. Is it? Surely you know what it is. So click on the correct one. We're not going to say it again. We have been saying it for the last hour. Okay.
I did definitely answer that one a few times. Hey,
yes.
Yeah, that's what we've been talking about.
Yes, like, come on. We even said how to color the invisible. You know. Right. So, question 3. The first image released from JWST was showing what is it? Okay, this one hint, it has 3 points. So here are 4 options. You can click up to 3 and you can be correct. Okay. Ooh, so is it a cluster?
I didn't fully answer this question. Ooh.
Oh, I will see later. I will see.
But I did not.
This is hint.
There are 3 correct answers here, and I did not give you all.
Is it a cluster of stars? You know, if you remember what Rebecca said, we have this magnification. We see inside the galaxies that are far away. You know, galaxies are made of stars. So clusters of galaxies. Definitely. I mean, this is huge.
It's a galaxy cluster, yes.
Sorry,
I'm going to give them that one, yeah.
That was a given. Is it a gravitational lens? The edge of the universe? Well, okay, we didn't see the edge of the universe. Because, you know, the universe be flat, but we won't see the edge. Mm-hmm. In the same way the flat Earth is. I'm sorry, that sounded better in my head. That was horrible.
Go on. Okay, all right. Anyway, next question.
That sounded better in my head. Erase that. Take my degree away. Okay, who is not part of the JWST operators? Okay, so if you saw these releases, the data releases in the summer, in July, was it? The first
I did
images.
say this too.
Okay, we had the NASA press release, but there were some collaborators. So we want you to select the one that was not in the mix. And if you don't know JAXA, this is the Japanese space agency. NASA is the USA. ESA is the European Space Agency, and CSA is the Canadian Space Agency. And shall we help? Okay. Let's
I did say this. I did say this.
You didn't say this. No.
I did.
Ah, you did. Okay. It is in, let's say that they're all very nearby. That doesn't help. Let's say I have, no. Okay, I will say it's not the first one because, okay, I like you guys. I will tell you. This is not the Japanese face. This is a very particular question. You have to know it. Usually, NASA and ESA collaborate a lot, or ESA and, and the CSA, they usually collaborate. So this is a nice collaboration, but not only from this, there are a lot of institutes, right, that play a role in developing this. Right.
So with JWST, I will just say, so it is NASA driven, like we are, controlling it and doing all those other things. We've built some of the instruments and the actual spacecraft itself. ESA has built one of the instruments and has also provided the rocket that launched it into space. And the Canadian Space Agency has also built some of the instrumentation and some of the other parts that are on the telescope. And so it truly was an international collaboration to make this observatory possible and to get it into space and operational.
Yes. Very nice. And we're all about collaboration. Right. So question 5. The primary mirror of the JWST has a diameter of 65 centimeters, 6.5 meters, 16.5 meters, 65 meters. Maybe the next one will be 65.
I really want that last one.
65 meters. Like, the whole Lagrange point, all of it.
Yeah, just a fleet of telescopes.
I don't know how big is the Lagrange point. I would be interesting to know, but all of it.
Just put a giant one on the moon.
Yeah. Yes, let's put a giant on the moon, on the far side of the moon. Why not? Yeah. Why not?
But right. Yeah, so you can actually see here is a really cool, like, kind of. I'm going to just talk about the things. What I'm talking about with Hubble being, low resolution at these wavelengths is because the difference in the mirror sizes. So visible and ultraviolet wavelengths are shorter, and so they can be high resolution with a smaller mirror. But infrared wavelengths are much longer, and so, like we said, the higher resolution is the ratio between the wavelength, the size of the wavelength of your light, and the size of your mirror. And so, for us to get these really high detailed, high resolution images in the infrared, we needed a bigger telescope. And it turns out that a telescope that size didn't quite fit in any of our rockets. And so part of the reason it is not a single mirror, like Hubble, is because we had to fold it up. And so we had to fold it up and then stuff it in a rocket and then launch it into space. And then the telescope had to unfold itself as it traveled 1 million miles past the moon to L2. And so this mirror segments here, the two on the side actually fold back. I don't know how that's like inverted on my screen, whatever, right? So like you have your mirror and the two sides actually fold back. And so you have a much smaller mirror size, and then it opens up to be the full mirror. And some of the first things they had to do was make sure that each one of these mirror segments was, actually like lined up. And so all of them were pointing at this. There's a secondary mirror that comes off. So you have your mirror, and then there's a secondary mirror that's attached. So all the light needs to point at that mirror. And then the secondary mirror directs all the light through this gap here into the instruments behind the mirror itself. And so they needed to make sure that every single one of these 18 segments was like pointing precisely at the place it needed to point at, so that all of the light was lined up. And there's some really cool images at the very beginning when they were doing all of this, where they were trying to focus the telescope, where there's we didn't know this. We didn't know this. They kept telling us the last time you'll see this telescope is when we put the little lid on the rocket, and they lied to us because when it launched into space, there was a camera on the thing that showed it starting to drift away. And that was when all of us started crying. And then this whole like little solar panel came out and we saw it move in space on camera. And I was like, oh my God. Right. So, but you know, and what they also did not tell us is that there is a camera on the secondary mirror that points and takes a picture of the telescope. The telescope takes selfies all the time to make sure that it's focused. And so I was like, oh my God, we're actually looking at the telescope. And so as they were, you know, trying to make sure that all these mirror segments were aligned, what you were seeing is they were pointing at a star, and like if it was pointing at the star properly, that mirror segment was all bright and lit up. And you could see as they were trying to get all of the other mirrors focused, they start to get them all like reflecting the light of this star. And I think those are some of the really cool images as you're seeing them physically move every one of these mirrors to make sure they are so precisely aligned. And, you know, every one of those things that moves needs to work, and we can't, you know, go fix it. It's way the hell out there. And so it needs to work properly. And I think, you know, I have not mentioned how terrifying it was to watch this whole process happen and not have, you know, like anything could have gone wrong at any time. And all of the things could have just broken because of it. And it was an incredible feat of engineering and truly phenomenal. And I am still like waiting for something to go wrong in a way that is like, this couldn't have been so perfect. This is operating better, and you know, everything went perfectly. And that's truly insane. And it was delayed so long to make sure that that was possible. And I don't know about you, but I am glad that we waited and that it works, because if it hadn't worked, that would have been the end of a lot of things.
I mean, you don't want to waste all these billions of money and effort of 20 years in the making. You know, you have to make sure it's gonna be okay.
Paid off.
And the Hubble mirror is like a meter or something, right? How do you remember? 3 meters.
Yeah, some meters. I don't know the actual. I should know.
It's like double and a bit. I'm just trying to help.
It's
right.
Doubling a bit. Yeah, that's a good.
Yeah, doubling a bit. There you go. There's your answer. So it's the second. All right. Right. So now Rebecca has answered all the following questions, and now you know them. Great. Very nice. But this description was amazing. I'm so happy you describe it with so much passion. It's amazing. It's awesome.
I am not seen this question.
This is great. Right. So next question, 6. The 5-layer sun shield is like having, she did not answer this one, but
I did not, but I'll talk about it.
You did not, but you can guess, people. Okay. So it's like having a sunblock of SPF 1 million. Don't Google it.
Can we real quick scroll back to the like little picture that you had of the telescope? Yes. Because I do want to talk about this too. Sorry. I don't know how long this telescope will be, but I will talk about this telescope for 100 years. Okay. So you see how like what we were looking at was the mirror is the gold segments. And so what I'm talking about with the secondary mirror is that thing that's attached to
this one.
Those things, right? And so then that mirror then reflects the light back through that hole in the mirror segment into the instruments, which are sitting behind the mirror itself, right? So the actual instruments and the cameras and everything are behind the mirror. And so what you're actually seeing here is this purple part, that's the sun shield. And then underneath that like round part, that's kind of the like the spacecraft that moves it, right? So all the little things that kind of like move the telescope around. And then the square part right there is the solar panel that keeps it charged. And then there's like a little doohickey below it, like right to the right of that. And that's the thing that talks to us, right? So what we need to do is we need to look at the infrared. And well, actually infrared is like heat, right? So if you've ever looked at, you know, I don't know, a video game or through night vision goggles, that's looking at infrared. We emit heat, which is radiation, which is lights, which is infrared light. And so what we really want to do is study infrared light out in space, but unfortunately the moon is warm, the earth is warm, and the sun's pretty pretty warm, you know. And so what we want to do is we want to make sure that we're not detecting ourselves, that we're taking all of that heat away from the telescope so the telescope can stay cold, and any of the things that it's detecting is not the telescope itself, it's not being warmed up by us or the moon or anything like that. And so what we have is you know, this telescope, if the moon and the earth are here, it's facing away from us, and that sun shield is always between the moon, the earth, and the sun, right? Because it's moving with us around. And so we always have this sun shield between us and the telescope. And it's several different layers, because every single layer is going to dissipate a lot of the heat from the sun, the earth, and the moon. And so like we needed to have multiple different layers. And so one of the other things that needed to happen was not just the mirror to unfold, that whole freaking arm to like come out and like make the primary mirror like snap into place, but this sun shield itself was like all folded up and then squished together, and it needed to expand out, and then it needed to tear up and expand. And so we have several layers of this sun shield, and we needed it not to tear. All of the things needed to work. And so we have all of these different layers because every single one of them is going to remove more and more of that heat or infrared light from the whole like earth, moon, sun system that is behind the telescope. And so the purpose of this sun shield is really truly to remove any of the light from us and the sun and make sure that the telescope stays cold out in space.
Awesome. So now you know the answer. Is it's a million. I would love this sunblock in the summer. I would not get any spots anymore.
I know, right? I mean, the sun are not friends.
This summer has been very cruel to me. I've been good. So JWST is 3 stories high and has the size of a tennis court. What is it, Rebecca? Yes,
it is. It truly is. The whole telescope is so big. So Hubble itself, the whole thing, not just the mirror, but the actual whole telescope is like the size of a bus, right? And so it fit inside the shuttle, and we put it, you know, up in space, and it's orbiting Earth pretty closely, just like kind of like right up there. You can actually see it from the ground if you know where to look, and it's dark. And JWST itself, the whole thing, sun shield, the whole thing is like the size of a tennis court. So the whole thing is much bigger than Hubble, and it's not just the mirror size. And so again, we didn't have a rocket that we could put a tennis court in and it would fit. And so we're just going to answer all of the things, but like we did have to, we did like, so instead of being like, oh, I guess we'll just have to make a smaller telescope, the amazing engineers were like, let's just fold it up and then unfold it. And so it basically is just a giant transformer in space as it like gets launched out and then unfolds and like kind of puts itself all together as it travels 1 million miles past the moon. And that, you know, this telescope launched Christmas Day, December of 2021, and you know, traveled for and unfolded and did all the calibrations and everything for about 6 months. It was going through this whole process of getting to where it was going. It took about like a month to get out there, and then the rest of the time was unfolding and testing and focusing and calibrating all the instruments and all this other stuff. And so, you know, this was it's a really intricate and like difficult machine, you know, and I think that like ultimately it's really, oh, thank you, 2.4 meters for Hubble. And so, you know, I think that it's really important to also point out that like there are a lot of people that made this happen, and they aren't astronomers. They are engineers, and they are scientists, and they are project managers, and they are, you know, press people, and they are people who are fundraising, and they are all like, it took so much of a human endeavor to build something so insanely complicated. And this is the first time we've ever done anything like this at all. And it fucking worked. Sorry.
Yes.
Like, it worked, right? Yes. Like, I mean, it worked, and it worked better than our best predictions. And that is insane. It's insane, and it's phenomenal, and it is incredibly inspiring. And I am so glad that we got this to work, because this, if you think about it, is crazy. This is crazy. This is a crazy thing to do. And,
folding a tennis court and taking it to space and unfolding it is insane.
Right? Yeah, it's wild. It's a wild thing to do, and it worked. And it's, you know, again, nothing that's ever been done before. And so there was like technologies that were created in this whole process just to like make this happen. So I think there's a lot of really cool stuff that happens from like us being like, we want to look at space, and then like all of these technologies have to be created to make that happen, you know. And I think that that's a really cool other side effect of astronomy and space and things like that.
That is true, and not the general public doesn't really know most of these things. The International Astronomical Union, I think, published an article a couple of years ago about what technology has made it into everyday life, like Wi-Fi, guys, Wi-Fi. Astronomers did that. Ceramic hobs, the MRI, the
Your
GPS.
cell phone camera.
Sorry?
Cell phone camera. That was
Yes,
us.
the CCTV cameras in our phones and etc. etc. And you can also read it in my Greek book because I wrote one.
You wrote a book?
I wrote a book. Yes. It's called The Universe in Your Pocket, and currently it's being translated into English. So hopefully,
Let me know when it's in English, because
yes, I will. So it has a chapter about all this, technological developments for astrophysics that made it into everyday life. Okay, parenthesis closing. Enough with my self-promotion. You should buy the book. Right. So the next one, JWST had to be folded in order to fit in the rocket of 5.5 meters wide. Okay, I think we extensively covered this one. Extensively. Was it folded? Really? Was it folded? Was it?
Yeah.
Right. So this one now. The primary mirror is made of how many hexagonal segments? So these are the little pieces you saw, and also in the necklace that Rebecca is wearing. These are the hexagonal segments. So how many?
I honestly just said this one too.
So this is difficult to know, and you can see the image before and start counting. I'm not gonna read
that is an accurate picture of the mirror.
You should know already. Okay, we had this picture out for like 10 minutes. The JWST was first planned to launch in 2007, 2011, 2014, or 2018. There is only one right answer. But we did not launch at that time, right? It took a long time after that. Not that long. Okay, it didn't take 10 years, okay? It's more like 2 or 3 years. It was set for...
originally planned to launch, or the first actual launch?
The first actual launch, I think. 2018, right?
Yes, it was supposed to be my PhD, but here we are.
Yeah, Oops. Now it's gonna be your Nobel Prize.
Oh, okay, no. Well, I mean, I think like we said, it's been a very long process. It's been 20 years in the making, from concept to building to all of the things, and it was supposed to launch in 2018, and we had even had a call for proposals to use time on it, which was a whole thing, and and it ultimately ended up having to get delayed because there was an issue, and again, we needed to make sure that it worked because we can't go fix it. And so I think it was devastating, and it was terrifying, and it was frustrating, and it changed a lot of people's career trajectories. But I think, I mean, again, I would rather have a telescope that works than a telescope that's early. So
yeah, or
it launched in 2021 in December.
Yeah. Right. So the assembled JWST had to unfold on its way to its final orbit. You must know by now, okay? You must know. I'm not answering this. While being transferred to the launch site in French Guiana, did I say this correctly? The circumstances of this transport were secret because there were fears about aliens, nerds, many nerds indeed, hipsters, or pirates. So what are you afraid the most?
This was actually weirdly stressful in a way that I didn't anticipate. And there's also a game. Someone made a little video game you can play.
Oh, really? I didn't know.
I don't I don't know where the link for it is, but there what so in order for us to take the telescope from the facility in California where it got fully assembled to where it launched from in French Guiana, it needed to get over there and it needed to like do so safely, and it was put on a boat. If that helps give you a hint. And
so it was definitely hipsters.
Definitely. I mean, the nerds really are the problem.
The nerds were already in California.
The nerds were on the boat. Yeah. No, so
right.
Yeah, Charlie, the telescope itself is not that cold, I don't believe. I think it's man, it's supposed to be pretty cold, but I'm not sure. There's actually a place you can go to look at like the current like temperature and stuff like that, and I think it's something on like webtelescope.org, and then there's like a where is web, and it shows you kind of all of the like what it's at right now, and it should show you the temperature and all the other stuff. It's just like a constant tracking of where it is and what state it is in. I think it's a little bit warmer than 3 Kelvin. 3 Kelvin is like pure empty space. But I don't know.
That's
It'd be great if it was that cold, but yeah.
For the next quiz, a very interesting question for the next quiz.
I'll keep answering all of them, yeah.
Yes, good. Right. So now we are in the next one. The JWST is like the Hubble Space Telescope, designed to get maintenance by a service mission. True or false? You should already know the answer to this. Rebecca has said it. And also, L2 is very far away. Very, very far away.
A million miles away.
A million miles away. It's even a song. So, you know, think. Can we go? Can we?
Yeah. No.
I'm going to take my rocket now. I have it parked on top of my house. I'm going to take my rocket and go and have a look. Right. Do we have more? We have a few more. Right. JWST is designed to find the birthplaces of planets, first stars, and first galaxies.
I didn't even talk about that first one.
So
I said I didn't even talk about that first one. I think probably one of the really pretty and maybe like cooler images to look at was one of the first release images where they did the Carina Nebula. And so like places where stars are forming, the birthplaces of stars and planets in our own galaxy are like clouds of dust and gas and like these like nebulae of really beautiful colors and things like that. And so I think yes, that is one of the things that JWST was built to do, is because in the infrared we can see the gas and dust that's in our own galaxy, and we can look for where these stars are forming. And you know, I think right now, perhaps maybe one person who is studying like the Orion Nebula has already shown that we have like the actual picture from JWST of a star in the little disk that's forming around it where planets are forming. And it is an insanely wild, very detailed picture of this solar system, planetary system being born, like in the process of that. And I think that you know, like there are so many different aspects of astronomy that are you know being like truly, again, I'm going to say revolutionized because of this telescope, because, you know, again, we're able to study details and get high resolution images and spectra of things that we haven't been able to study like this before. And again, like the MIRI instrument operates at wavelengths that we just haven't seen, and it's insane and it's phenomenal. And so yes, all of the above and more.
MIRI is wild.
My God,
I read on Twitter. MIRI is wild. I think you wrote it.
Oh.
Was it you? Someone? Maybe it was you. MIRI is wild. That was
yeah, 100%. That was me. I have, every time that they have come out with press release images of any of like the big press targets, they've led with the NIRCam images because they're the highest resolution, whatever. And then they're like, oh, and also MIRI. And then I just freak out because this is truly something we have never seen before, is the MIRI infrared is like longer infrared wavelengths. And so we don't know a lot about that. And I think some of the really cool stuff that's going to come out of this telescope that I didn't fully appreciate, because predominantly my science is NIRCam, is that instrument on the telescope. And I've been freaking out about MIRI more than I ever expected. And some of the spectra that are, oh my God, the whole thing, it's just, the whole telescope is very exciting, and I'm very excited about it. Yeah, anyway, what's the question?
I wish I had a song now to play. But yeah, let's go to the next question. Sorry, here you go. JWST was able to study the atmospheres of exoplanets. What chemicals has already found? Carbon. So this one has 2 points. So you like 2 correct answers. Carbon dioxide, water in the form of clouds, methane, ammonia. I mean, one is already in front of your eyes. If you don't pick that, then I don't know what. And the other one, well, one of the things we want to find is, science for life. And for life, you need oxygen, you need hydrogen, you need water, right? You don't need methane. We cannot live.
Maybe you do.
Maybe we evolve.
We don't know.
We evolved and we managed to survive in a methane atmosphere.
Yeah, I don't think we would, but that would not be fun. Yeah.
But anyway, yes, let's go to the next question. Thank you. JWST is discovering the most distant galaxies when the universe was around 600 million years old. That's very young. Okay.
I have a small caveat. I think it's about 400 to 300 million years old, is surprisingly how far back we've been able to see.
Yes, I want to see spectra from these galaxies first. That's why I didn't put that. December. This quiz will be updated for the December release with the Cosmos data. But guys, I was a bit conservative because, yes, we have seen galaxies at redshifts of 13 and 14 and whatever it was. That is insane. Mm-hmm. But I want to see spectra of these things. So same. This is conservative.
We have follow-up spectra planned for our SEERS program, right? So we only got like less than half of our data in July before the telescope could no longer see like our thing that we were looking at. And so we have spectra that are coming in, and we also have, a proposal that got put in to get more specific spectra of these galaxies that we've been finding. And we also have proposals to look for them in radio wavelengths to see other things. And so we are trying to follow these all up with spectra so we get actual very precise measurements of their distances, and to truly understand like what it is that we're seeing with JWST, and to try to confirm what we think we're finding, which is exciting in all these other things, but also is really, really important. And right now it is, only a few months. It's like 3 months since we've been getting data, and so any of the things that we're finding, we're trying to make sure that we're confirming, and the best way to do that is with spectra, but spectra is also much more difficult than just taking images. And so we are building up all of this information, and hopefully by like a year from now, we're going to have a whole bunch.
Absolutely. And just to mention that in this image behind me, they found one of these very distant galaxies at 13.1 billion years back, I think, if I remember. So this is the one that is quoted here. Mm-hmm. And this was the first one, okay? So after that...
I cried when I saw that spectrum. I thought, oh my God, you gotta be kidding me.
I'm glad this was so enjoyable for you, and all this.
Oh my gosh, it's been emotional.
Yeah. So all this weight was how do you go? Sorry, my Greek is interfering with my English. It paid off. Sorry, it paid off. All this weight.
Yes, it really did pay off.
So so I have 2 more questions. Okay, let's do this. JWST revealed in great detail the rings of which planet shown in the image. So this is only one planet, and you have to find the correct one. And already Rebecca said it, okay? So you better...
Sorry.
No, it's great because it's great. It's like, it's like in the classroom. The teacher does the course and then the quiz comes and like, but we said it in the class. Why didn't you?
Yeah, so I know, I mean, Saturn is personally like my favorite and like the best planet, but you know, and it is famous for the rings that it has, and you can see them from your backyard with a very small telescope, and it is, to me it was incredibly like mind-blowing. But it is not the only planet in our own solar system that has rings around it, and so it turns out that there's quite a few of them, and we have known about this, and we have seen these things from other telescopes, but getting a really cool picture from JWST and truly being, I mean, the detail is crazy. And I think even more insane is this picture. I encourage you to go like look up the images of this planet with JWST. I was like, oh, with JWST, because what you're seeing is the actual image is quite large, and this planet is just here, and like you're seeing it on the backdrop of space, right? I mean, there's like galaxies in the background, which is insane, but like you can actually truly see that this planet in the frame of the image is very, very small, and you can see it's just like, here's our little solar system planet and all of space behind it. And I think that was really, truly like an incredibly eye-opening, I guess, way to look at it. Like all of the times we see these zoomed in pictures of the planets and it's like all the details, and that's really cool. But I think also important is to back out and look at it kind of more like in context of like we're here, and like there's all of this other stuff out there, and we're pretty small.
Okay, I will help a bit. All these planets have rings.
I was going to say every single one of those.
I help you so much.
And we have taken an image of Jupiter with JWST, and we do see the rings. We see the rings of Jupiter in the image that we took with JWST as well.
Yes. And Jupiter is much bigger than this one, so it's not Jupiter.
And much closer.
We know it's not Saturn because Saturn looks a bit differently. So it's between, as we say it in Greek, Uranos, because if I say, I don't know how to pronounce it in English. There is a bad joke about it, so I won't. My kid watches TikTok all the time, and this keeps coming up on the TikToks, so I'm like not saying it in English anymore. I will say it in Greek, Uranos.
Perfect.
Which means sky, by the way, or Neptune. And just to say that is the first time we see these rings from a telescope, because the other time we had actually seen the rings, it was from a probe that went to this very far away planet. That is the furthest planet of our solar system. Okay. Now you have to, come on. It's the last, isn't it?
Not Pluto.
Pluto is, unfortunately, it's not a planet. It's a dwarf planet because we don't play with it anymore. We are bad people.
But JWST is taking spectra of Pluto right now.
Oh, awesome. Okay, I want to see this.
Right now, I mean, we're taking actual spectra of Pluto with this telescope.
Awesome. Amazing.
So we've had these beautiful images of Pluto from the New Horizons telescope probe that went by it and took these phenomenal pictures of this insanely detailed dwarf planet and its companion out there like super freaking far away. And now we're getting spectra to truly understand and get detailed information about like what is it made out of and all this other stuff that I think is really, really cool. And so that data will be coming out. I mean, like there's new data every freaking day, right? And so like there's actually a bot on Twitter that tells you what the telescope is looking at, and that is how I found out that one of our programs was being observed. I was like, wait, are we getting data right now? Wait, is that happening right now? And I was like, oh my God. And then I was like, wait, guys, we have data. Why did no one know this? And it's because thanks, Ryan. They've been like super good at scheduling everything, that we've like worked in some kind of like buffer to make sure that we're not going overtime, that we could fit all this stuff in the schedule. And everything has been incredibly efficient, such that they've been able to move programs up that were scheduled for much later, because they have like room in the schedule to do more observations earlier on. And so I think we had one of our programs that was scheduled for like next year moved up, and we had like 3 days notice that you're getting more data, and we were like, oh god, so it was,
that's good, you got your data,
super good, but also like I was like trying to do this other stuff, and like I was like, I didn't know where. Oh my gosh, it's a great problem to have, and I'm really, really, truly impressed by everyone who's been working on this. The whole telescope, the observatory running it, and all this other stuff, because they've been so good and so efficient, and it's operating amazingly. And Ryan here in the chat is one of those people. So I truly appreciate.
Hello, Ryan.
Yeah. Mm-hmm.
Congratulations, Ryan.
Yeah.
And just to say about Pluto and these faraway systems in our solar system that are not complete planets yet, they help us understand how planets are formed, and they are in the outskirts of our solar system, where you have other rocky objects and where asteroids and comets come from. So by understanding what they are made of, we learn a lot of things about how the planets were made and about all our solar system. So it's not just watching at pretty objects, we get a lot of science out of it.
Yeah.
So, oh my God, okay.
Oh, we did it.
We did it. I will not reveal how many you got right because of data protection, but I will send the emails to everyone separately with congratulations. And before we do the last one, congratulations to everyone anyway for your effort in taking the quiz. I hope you enjoyed it and enjoyed Rebecca's explanations, and thank you very much for that. Oh, he's so sweet.
Oh yes, this is Jasmine. This is my sister's dog.
Oh, hello, Jasmine.
She's gotten tired of waiting for attention, so she's here for it now.
Very nice, very nice. We're almost done. Sorry for the wait. Last one. For the first time, JWST and Hubble took a simultaneous image of what object? Okay, guys, if you were 2 weeks ago, okay, I know we get things every day from the web, like every single day, and there's a lot of information out there, but 2 weeks ago, something spectacular happened, NASA mission. So for
perhaps
the first time,
maybe it was called DART.
Yeah, maybe it was called DART.
But I won't tell you what that stands for, because the answer is
yes, we won't tell you. But it's awesome because they actually targeted the same object on purpose, okay, at the same time, just to see what's gonna happen. Is it gonna blow up? Is it gonna not blow up? Is it gonna move from its orbit? I said a lot. I said too much.
Yeah, so this is actually really cool, because both of these telescopes are looking at something that's moving pretty quickly, and they're looking again at different wavelengths. So we're studying the same thing at the same time. So we're looking at something at multiple wavelengths simultaneously, which is really cool because you're seeing different parts of what's happening. Both telescopes are experts in different parts of the wavelength, and I think it's really cool that not only do we get like these pictures, but it was not just Hubble and JWST. It was Hubble and JWST and ground-based telescopes and all kinds of people just with their own telescopes at home we're looking at this event all at the same time. And I think it was really, really cool to see how much information that we can gain from incorporating all of the facilities and all of the telescopes and things and all of the people and in trying to understand and learn something new. And so if you are interested in this, I would highly recommend you Google NASA DART mission, because it's fun what the animation does, but also because it was a really exciting, really cool thing that happened.
And that's the first test for planetary defense, let's just say. And that is all I will say. So that was the quiz. Let me stop sharing. Congratulations, all. I will reveal the results.
Oh, what? There's a DART press conference going on right now?
What?
We gotta go.
Wow. Okay, I didn't know that. Sorry for not looking at the chat before.
You're fine.
Yes.
Charlie, it's not about being smart enough. I think that's a really good question. But yeah, Ryan, it was in like all kinds of chambers, and there's all kinds of stuff and things that we've learned about launching stuff into space and about how to keep problems like that from happening. And I will not speak much about it because I am not an engineer, but damn it, Jim, I'm a scientist, not an engineer. Yeah, so yeah, that's a good question, and I'm glad that like you're thinking about it, because it is something that we definitely had to consider when doing the telescope and putting it there.
So we're approaching the end. My kid is anxious, to play Pokemon, so he needs my phone. I have to terminate this live.
Yes.
They cannot see you. You have to come closer. You are back. You're too far back. Not even JWST can see you. This is Aris. This is Rebecca. Hi. Oh, you're lost.
You're in space.
You are in space. Oh, be careful. Okay. Yeah. Excellent. Now he has my phone. He doesn't care. Go. I should have given him my phone at the beginning of this.
That would have worked too. Yeah.
Yes. But anyway, thank you so much. That was a blast. I enjoyed this so much. You cannot imagine. Really, it's such a pleasure talking to you. You talk with so much passion about what you do and about. I know. Go inside. About what you do and about James Webb and what interests you and what interests humanity and how they interlink and the whole concept of why we should get out of our, labs or desks and talk to people. And I love that. So I hope people at home, you got inspired.
Stay tuned. We have some really cool science coming out from our programs. I can help Eleni put some of the links for some of the things that we've been talking about down in the YouTube, whatever description thing afterwards.
Subscribe.
Hit like, subscribe, whatever. Right. So I think, there's a lot of really cool science coming out. Our team has an image that I really, really encourage you to go take a look at and to not download on your phone because it's very large. And we'll put the link to that there. That's on our website at sears.github.io, which is a terrible link. But yeah, so I think there's some really cool science that like we're doing as far as like distant galaxies. There's plenty of other teams who have data coming in. Like Elena mentioned, there's the Cosmos program that's going to be taking data in December, starting to take data in December, and they're going to build the biggest. We have the biggest picture right now, but you guys are going to make the biggest, picture, like actually like tile along the sky and not have any gaps in between. And that's going to be really exciting and really cool to start to see build up. And Eleni's running a lot of the like press and outreach and stuff like that for that. So please follow her and all the things that she's doing, because there is some really, really, really freaking exciting science and some beautiful images coming out. Like I've been trying to share them on my like Instagram and Twitter and things like that if you want to follow me. But ultimately I truly encourage you to keep paying attention to some of the stuff that's coming out of JWST, and not just the pretty images, but some of the really revolutionary science. I think it's phenomenal and exciting. And I think I have never seen the world more excited about, things that happened 13 billion years ago than I have recently. And that's been a lot of fun. So thank you for having me and for doing the show. And I appreciate the opportunity to come and just ramble about JWST forever. And so, I think it's really, really important that we keep these things going. And again, if you have questions or whatever, feel free to reach out to either of us. We're happy to chat with you about space. This is why we do what we do. So is to answer questions and share the answers with everyone.
Excellent. Subscribe, like, follow, everything. Just to let you know, guys, it's not only YouTube. You can follow us everywhere in the whole social media universe. TikTok, okay, at
Ooh, I don't have that
aotjena.
one. That one I'm not
TikTok.
sure, yeah.
TikTok, awesome. TikTok, Facebook, Instagram, Twitter, and YouTube. Okay, so get in contact, watch the previous videos, watch this one again because it was super awesome, and see you next month with more amazing science.
Awesome.
Yes. So now I have to manage to stop this live. Ah, there you go. I found the button. Sorry, I told you I have a little stress first time.
Good.
Have a good night and see you soon, guys. Ciao. Bye.